Hello, good morning, good day. My name is Marcelo Finger. I'm a professor of computer science and at the University of São Paulo. And it's an honor for me to present Isabel Trancoso. She is a leading researcher in voice and spoken language processing. She is currently at IST in the Department of Electrical and Computer Engineering. She had a PhD there from the same department, and she was for some time the head of the Electronic and Computer Engineering Department at IST. She was previously the editor-in-chief of the IEEE transactions on speech and audio processing, and she's currently an editor of IEEE proceedings, and she has, well, a few hundred papers published on top journals and conferences in spoken language and voice processing, and it would be an honor to hear her speak about speech as a health biomarker. So, Isabel, it's an honor to have you here.
Boa tarde a todos, ou bom dia, conforme a hora que me estejam a ouvir. É um enorme prazer, uma grande honra para mim estar aqui. Agradeço imenso o convite ao Abralim, em particular ao Miguel. Eu gostaria também de pedir desculpa por fazer esta apresentação em inglês. Torna-se mais simples, uma vez que todos os materiais estão nessa língua. So, switching to English.
Sorry, Isabel, the slides are not in full screen.
Okay. For me, they are. So let me try.
It's in presenters mode right now. You have to turn it into presentation mode.
Still the same?
We can't see it.
Yeah.
There's no projection.
I know.
Okay.
What about now?
Yes, great, thank you.
Okay. So, switching to English, I'd like to start by stating that this is joint work of my PhD students, Joana Correia, Francisco Teixeira, Catarina Botelho. This is your work. Thank you for this. And my co-advisors, their co-advisors, my colleague Alberto Abad, also from our engineering university, IST, and my big friend, Big Sharaj from Carnegie Mellon University. So talking about speech as a health biomarker is one of my favorite topics. In fact, I also like talking about the fact that most speech and language technologies can find an applications in e-health. Sorry. Seems to be stuck. cannot move it.
Try to click on the slide.
Yeah, now I got it. It was on the wrong screen. So I was saying that I also like to say that, to claim that most speech and language technologies, like the ones shown here in the slide, can find applications in e-health. So today, the technology that I'm most focusing on will be speech analytics. And this covers extracting all the information from speech that's beyond text. So I mean by this the speaker ID, the gender, the generic age range, the language, the accent, the degree of nativeness or non-nativeness, the emotional state, whether someone is angry or happy or whatever, personality traits like introvert or extrovert, stress, intoxication by either drugs or alcohol, degree of sleepiness, cognitive load, physical traits such as height, and also the topic of today's talk, speech affecting diseases. So what do I mean by speech affecting diseases, for lack of a better term? The scope is much broader than what they are, the so-called speech and language disorders like astigmatism or stuttering. What I mean by these speech affecting diseases is diseases that concern respiratory organs, like, for instance, the common cold or obstructive sleep apnea, that we'll call OSA from now on, or mood disorders such as depression or anxiety or bipolar disease, and also neurodegenerative diseases like Parkinson's or Alzheimer's or ALS. So there's an enormous spectrum, and the way they affect speech can be very diverse. Let's illustrate this with OSA, for instance. Patients suffering from OSA typically show articulatory disorders causing slurred speech, phonation anomalies, mostly due to the fact that they frequently snore, and that causes larynx inflammation, and also resonance anomalies due to the fact that there is a abnormal coupling of vocal and nasal tracts. On the other hand, patients suffering from disorder, typically from depression, typically have dull speech, monotonic, monoloud, lifeless, metallic, and patients suffering from Parkinson also show dysarthria, difficulties in articulation, reduced loudness, hurried speech, and also difficulties in swallowing and excessive salivation that are also have an impact. So all these symptoms can be automatically detected from speech. So the potential of speech to act as a biomarker for speech disorders has bolstered many studies on their automatic detection based on the powerful machine learning classifiers that either operate on the basis of features extracted from speech or directly on the signal itself. These are the so-called, very popular nowadays, end-to-end new deep learning approaches. In fact, it's not only the research community that realizes this potential, but also companies. And it's worth mentioning that back in 2016, IBM already had in its prognosis of what will be the five most disruptive technologies 5 years from then, already had a sentence say, with AI, our words will be a window into our mental health. So this shows that the potential is here. And the fact that speech is ubiquitous and can also be acquired non-intrusively makes it a very inexpensive modality. And so it can be used for early screening, and early screening may be really important to seek immediate medical assistance. On the other hand, besides being potentially useful for diagnosis, it's also potentially very useful for monitoring. It can be used both in clinical facilities or at the patient's homes remotely. And so the progress of the disease can be monitored to adapt medication or any type of support. And this can be important given the usually long interval between specialized medical exams. Despite all this recent progress, the potential of speech as a biomarker is still very far from being explored. And in this talk, I'm going to address two aspects that, in my opinion, have not yet been sufficiently explored. One is the fact that most of the data sets that exist for these speech data sets that exist for these diseases are rather small and collected in controlled conditions from patients diagnosed with the given disease and the healthy controls. They do not contemplate recordings made in the wild conditions, but if we want this to be broadly used, we have to take this into account. And on the other hand, the potential use as a biomarker for health condition also raises privacy issues, namely when this type of analysis is performed in remote servers. So these are the two topics of this talk. First, I'm gonna address the in the wild aspect and tell you about how we collected this in the wild data, speech data, and then I'll address the patient privacy issues. Let's now go to the first part, the in the wild speech medical corpus, the WSM as we called it. So we decided to collect this information, these videos, from a multimodal repository such as YouTube. In fact, we collected it from vlogs, video blogs in YouTube. Because they were videos of a single person, and we wanted to look for videos in which they somehow claim they were suffering from that disease. So the data set was collected using a combination of the official YouTube API and scraping tools to retrieve a list of results like the ones that I'm showing here, which were then annotated in order to have a data set for that disease, that speech affecting diseases. And we also did more generic queries such as vlog alone or daily vlog or Parkinson's lecture or something like that in order to be able to get data sets of potentially healthy controls. And after having the two data sets, our goal was obviously to have to build a classifier for in the wild detection of target diseases on the basis of the acoustic signal itself, disregarding all the linguistic contents of the message. So our corpus, the WSM, was restricted to videos in English. We downloaded the automatic transcription provided by YouTube, which was generally very good. It's a growing corpus. The pilot version that we built had only 119 videos, and we chose 3 initial data sets: depression, Parkinson's, and common cold. But I won't be talking about this third one because it was too much of an effort in terms of annotation by a single annotator. That was my student, Joanna. So I won't address this any further. We also built a very small pilot corpus for OSA, just as a proof of concept. Then we expanded it to have about 500 videos with more healthy controls. And after doing experiments that proved the validity of our approach, we then embraced on a big collection. Right now, the corpus has more than 900 videos, totaling 131 hours, and includes, that's very important, a balanced data set of healthy controls in terms of age range and gender. The data set comprises 277 positive videos for depression and 209 for Parkinson's. We also started very recently a collection on COVID-19, this nightmare that we have currently. And we had this corpus annotated by 5 Turkers using the Amazon Mechanical Turk platform. As I've explained, we collected from YouTube all the possible information that we could get, video identifier, title, dates, the transcription, of course, the comments, the description whenever there was one, number of thumbs up and down, all the metadata that we could get. This is the type of video vlogs that we were aiming at. So containing a single subject, claiming that he or she were suffering from that disease in the first person using the present tense. This means that we had to disregard, as positive examples, of course, videos that had multiple subjects, as typically not vlogs, talking about unrelated topics, sometimes lectures on Parkinson's, depression, whatever, or be videos from caregivers talking about someone else suffering the disease, or talking about their own past experience with the disease. So we annotated the first pilot corpus that had about 60 videos from each of the data sets. For all these characteristics, is it a vlog? Is it in the first person? Is it in the present tense? Does it contain the claim of suffering from the disease? And ended up with 18 positive only from each of these. But of course, it's a lot of work to do it manually. So our first effort after the collection was to try some automatic annotation approaches. We started with a fully supervised approach, in which we tried using all the multimodal features that we could from the info that we had collected from both the video, the audio, the transcription, and the metadata. We tried basing this on straightforward modeling paradigms, mostly off-the-shelf tools, and tried contributing how each feature, the impact of each feature separately also. So, as you can see here, we had textual features, speech features, visual features, and metadata features. And we tried 2 classifiers, logistic regression and support vector machines, and we made predictions for all the 4 categories differently. Is or is not a vlog, first, third person, present, past, and talking about suffering from the disease. The textual features were, as you'll see in the results, the ones that were most impactful. Mostly, especially the bag of word features that we could get from the video's transcription. We also had sentiment analysis features, but bag of words really did most of the work. As you can see here, the results in terms of precision recall of our best classifiers. You can see that the results for bag of words were very similar for both data sets than the ones that we got with all the features. Probably also because the off-the-shelf tools that we were using for other features were not so appropriate for this task. I don't know. And you can also see that the the question that was mostly hard to classify was the present past tense, especially for the depression subset. After this, we also tried weekly supervised approaches, and based on a generalization of the multiple instance learning paradigm, and also semi-supervised approach based on greedy set partitioning, both of them only considering textual features, but it's too much to cover here, so I won't even mention. After our initial experiments with the pilot corpus that showed that the self-reported health status is a good proxy for the true health status, we embarked on the huge collection that I mentioned with the annotation by Turkers. And you can see here the results of partitioning into train development and test sets for both the disease and healthy controls. And you can see number of hours, number of videos, and also broad age range and gender as much as it could be guessed by the Turkers. Having done this, in order to complete the pipeline, we have to now build the acoustic classifiers based on the speech signal alone and not about its linguistic contents. I stress this again. In order to do this, we contemplated using different sets of features, starting with handcraft features that we mostly call knowledge-based features from now on. In order to do this, we looked at the symptoms in speech that we had mentioned before and saw how they were objectively expressed. For instance, for depression, we knew that we were expecting a lower mean F0, a smaller range of formant frequencies, a reduced variation in loudness, higher jitter and shimmer, higher harmonic to noise ratio. So obviously these were some of the features in our knowledge-based feature set. For Parkinson's, we also had to use perturbation measures such as jitter and shimmer again, our articulation features like vowel space area, formant centralization ratio, etc., capstone features such as mel frequency, capstone coefficients, and also prosody features like pitch and energy contours over the utterances, etc. The nice thing about these knowledge-based features is that they are more easily explainable, making it possible to create bridges between data scientists and healthcare professionals. So that was very important to us. We also did experiments with generic feature sets for paralinguistic tasks. So finding health symptoms in speech is a paralinguistic task. And so we took advantage of the fact that researchers had got together to identify among all the myriad features that could be used, the ones that were more frequently useful for paralinguistics. And they put them together in something they call the GMAPS feature set, standard for Geneva Minimalistic Acoustic Parameter Set, that had about 60 something features. And then they extended it, now it's the EGMAPS. Both can be extracted with the OpenSmile toolkit that generates above 6,000 features if we want. And both these minimalistic parameter sets included functionals of low-level descriptors, that is parameters at the frame level that represented either spectral or capstral or prosodic or voice quality parameters. Mostly the functionals were means and standard deviations across the whole utterance. Another set of features that we also tried was bag of audio words. Also, there are very useful toolkits for this. They represent audio segments as distributions of low-level descriptors, but taken from a codebook, in some way quantized. We could have bag of audio words from capstone features or bag of audio words from the EEG maps themselves or whatever. And we also tried deep spectrum features, that is features derived from forwarding plain spectrograms or MEL spectrograms through very deep task-independent, pre-trained convolutional neural networks. But the experiments that I will report here are based on the most recent set of features that we tried, which is falls in the category of generic speaker representations. So rather than using knowledge-based features that may not represent the disease's full symptomatology, may even overlook some of its more subtle manifestations, researchers started moving in the direction of generic speaker representations that inherently model symptoms such as, I think that the earliest ones in this direction were Gaussian mixture models that adapted the distributions that were taken from a universal background model to particular speakers. Then there came I-vectors, which were a much less fewer dimensional space set of features that also modeled the environment and the channel in which the utterance was recorded, and more recently, X-vectors. And X-vectors are speaker embeddings. This means that they were obtained from a neural network trained to classify speakers in a training set. Mm-hmm. So the networks for extracting X-vectors have three parts typically. The lower part here, there is an encoder network that extracts frame level representations from the acoustic features, maybe even MFCCs, capsule features. This is followed by a global temporal pooling layer that produces a single vector per utterance. And finally, there is a feed-forward classification network that processes this pooling vector to produce speaker class posteriors, predicting the probability of each speaker given the input features. The X vector is this speaker embedding here that's obtained from the first affine transformation after the pooling layer, and just discarding the upper layers in the network. So our effort was to provide, together with the corpus, a number of reproducible baselines with which other researchers could experiment. And we tried this with features such as EEG maps, with classifiers such as support vector machines and deep neural networks. We tried bag of audio words features. We tried knowledge-based, of course, I-vectors with probabilistic linear discriminant analysis, and also X-vectors. We also tried MEL spectrograms and end-to-end networks, but I'll only mention the X-vector results, which are shown here for both depression and Parkinson's in terms of precision, recall, and F1 measure. Average both for the positive and negative classes in each data set. So this is what we typically call the unweighted average recall. if we compare these values with the values for UAR in data sets in controlled conditions with similar methods, but using only the same type of materials, that is read sentences or spontaneous sentences, but not things like sustained vowels or repeated syllables. No, typically just sentences, using only these sentence subsets. So we had these data sets, for instance, for Parkinson's, for Spanish and Portuguese. And you can see that the results that we got, although the classifier was different, sometimes are higher, sometimes are lower. That means that the results are typically different from data set to data set that cannot be compared. There are data sets that are more difficult than others, probably because they have more, I don't know, possibly borderline patients, I don't know. It's also important to mention that in previous experiments with other feature sets, we trained systems with controlled conditions and test with in the wild data sets. And of course that showed the expected degradation, but this is what happens with every out of domain set, and not particularly because we were using in the wild conditions. And we also tried mixing in the wild and controlled conditions, which also yielded promising results. At least we got reasonably good results for depression, which was the data set in English that we had. As a curiosity, we also did this for our much smaller data set for OSA, for obstructive sleep apnea, and even got better results for the in the wild data than for the controlled conditions data. We did this using knowledge-based features, other type of ensemble classifiers. But the interesting thing about this experiment for us was first to verify that whereas the controlled conditions patients were at their first medical appointment, so they had not started treatment yet, the WSM patients had already, were claiming they were already being treated for this, but the treatment does not alter speech anomalies. That's what we found. By doing mixed experiments with leave one out cross-validation in the wild and controlled conditions, we also could get reasonably good results, which was also proof of concept that this thing also works with cross-lingual data, because our controlled conditions data set was in Portuguese and our in the wild data set was in English. So the summary of this first part, I could say that we tried establishing a baseline for collecting in the wild disease-specific corpora of speech-affecting diseases by mining multimodal online repositories of blogs, concretely. We demonstrated the viability of the old pipeline process for some diseases, which led us to believe that the process is generalizable to more diseases. And it's also important to mention the very good behavior of the textual bag of word features for an annotation help, automatic annotation. And finally, also stress the fact that given that the whole pipeline is very modular, each component can be individually improved, and that's what we're trying to do now. Mm-hmm. Let me now turn to the second part, the second aspect that I also felt was not sufficiently explored, the patient privacy part. So the widespread use of mobile devices, cloud-based applications, social media platforms, and voice-based virtual assistants especially, has given companies and researchers access to an unprecedented access to data, amounts of data, and this allowed the development of very powerful machine learning classifiers for a number of applications. And cloud-based platforms use these models to provide users with remote machine learning as a service applications. But the widespread use of these applications also created a society-wide debate on how user privacy is maintained, is guaranteed by these online service providers. And regulations such as the EU GDPR, which probably you also are familiar with, have put forward restrictions on how such services should be used to handle the user data. Well, speech is a particularly relevant data source because it does not only concern the linguistic context, but also the paralinguistics and extra-linguistic information that may be extracted. As I mentioned, we can extract things like emotions, like gender, like age range, and the topic of our talk, health conditions. And health is particular worth protecting. So all this information is in fact private and should be protected at all costs. And we live, in fact, in a world where speech and the information that can be extracted from it may be regarded legally as personable identifiable information. So how did we address this? How did we make privacy-preserving machine learning as a service? So there are several approaches. Some of them we won't even mention, like federated differential privacy or federated learning techniques or secure enclaves. I won't mention them. Rather than talking about them, I'll talk about using breakthroughs in cryptographic techniques, especially homomorphic encryption and secure multi-party computation. It's not hard to understand the basic principle of homomorphic encryption. It's a family of cryptographic methods that respect at least one or more of the two equivalences below. What this means is that if we have a clear signal X and it's encrypted form, E of X, and we have a other clear signal Y and its encrypted form, the encrypted form of a multiplication is some operation on the encrypted forms of the isolated X and Y ciphertexts. And the same holds for addition. So this means that multiplications and additions can be rendered secure. The advantages of homomorphic encryption are that they only require two communication rounds between client and server. That's efficient. For performing linear operations like inner products, that's efficient as well. And there's also the possibility of encrypting many, many values in a single ciphertext. This is a technique called batching, which is handy in case we want to handle multiple files from the same speaker. So what are the disadvantages? Very, very high computational cost, and most schemes limit the number and type of operations that are allowed, otherwise the cost grows out of hand. How did we use this? So we took our neural networks and tried to make them privacy preserving using the type of a similar type of approach to what was suggested for images in CryptoNets or even in CryptoDL. The basic idea is to replace every operation in the neural network by the homomorphic encryption counterpart. That solves most of the operations in the neural networks except the nonlinear activation layers. And here we had to resort to polynomial approximations that may cause less accurate models. Because we had to guarantee that the inputs to these activation layers were within the region of convergence of the approximation, we also had to introduce some normalization, which required discretized weights and inputs and may also lead to accuracy degradation. So we were expecting some accuracy degradation. It was when we did experiments with controlled conditions. I won't show the results because it's controlled condition data sets, cold, depression, Parkinson. We did obtain a small degradation, but if we take into account all the utterances of a single speaker, at the speaker level, the degradation became almost negligible. The real bad part about this approach was that it took much, much longer to make a prediction than for an unencrypted context. That is, instead of microseconds, each prediction now took 4.5 seconds in the laptop of Francisco. And in order to amortize the cost of this doing simultaneous predictions, we had to use some 16,000 or so, which is not so interesting. But the problem is also that we couldn't experiment with really deep networks because the network architecture was limited in terms of computations and also noise growth. So we decided to turn to a different approach, concretely to support vector machines, which are handy for health tasks, speech health tasks, because typically the data is not that much, and SVMs are one of the most suited approaches for handling these amounts of data. The problem with the SVMs was that the most efficient kernel that we could use is the RBF kernel for most of our experiments. And the RBF kernel is computational complex. In fact, this kernel uses the computation of an Euclidean distance between two vectors. And this Euclidean distance implies squares, implies square roots. It's tough. So our first approach is to use some sort of distance preserving hash function. This is called the secure modular hashing, SMH, which instead of using the Euclidean distance takes advantage of the fact that we can approximate it with the Hamming distance. And because it's proportional to the Euclidean distance for small values of this distance, and it gives no information at all about the distance for when this Euclidean distance exceeds the threshold. So this is much easier because here we just have exclusive OR operations, much, much nicer. But in order to compute the kernel, we also needed exponentials. Again, we can resort to a polynomial approximation. And in order to compute the rest, we had to use a panoply of other cryptographic primitives like homomorphic encryption and secure multi-party computation like garbled circuits or secret sharing. I won't mention them, but it's just important to realize that it becomes viable to have an encrypted support vector machine. And in our experiments with control condition data sets for OSA and Parkinson's and knowledge-based features, we found out that the encrypted SVMs showed no relevant accuracy degradation relative to the non-encrypted part, which is very good. The predictions now took like 600 milliseconds at the cost of some communication between client and server. So we seem to have found a proof of concept of how these paralinguistics health-related tasks can be made secure. We tried this with ENNs and ESVMs. With the neural networks, we showed that it's possible to discretize an encrypted neural networks with minimal accuracy degradation, but we also found that we could not move to much more complex networks. The solution seems to be to alternate between cryptographic protocols, such as the cost of adding an additional layer is simply the cost of the layer, doesn't explode. And for the SVMs, we found that replacing the Euclidean with a Hamming distance with this secure hashing function was also very effective. And we didn't get any degradation. However, the computational cost and the bandwidth cost of communication of both these methods is still much higher than in the clear counterpart. And it's also important to mention that we are leaving all the work of feature extraction to the client, and maybe we'll have to deal with this pretty soon. So we have a lot of work in both these aspects to consider. My main take-home messages are that for diagnosis and monitoring, speech can indeed be a non-intrusive tool. We addressed 2 questions. Will such diagnosis tools work with in-the-wild data? And by mining multimodal online repositories, we tried showing that this was true. This was at least had lots of potential. And we also tried answering the question of whether these diagnosis tools, when performed in a remote server, could compromise the patient's privacy. And we found out that by using a combination of machine learning and cryptographic methods, we could obtain either slight degradation for neural networks or negligible degradation for SVMs with this radio basis function kernel, but at the cost of considerable computational costs. So we have plenty of work ahead of us, but I want to leave you with 2 open questions that are really very dear to my heart. And the first one is, how far are we from making the analysis of speech just as common as blood tests are nowadays for medical diagnosis? So we showed that, and plenty of other researchers show that it's possible to use speech as a biomarker for different speech affecting diseases, but I'm not talking about using speech to give a score that works as the probability of this person having this disease. No, I'm talking now about having a detailed view of different aspects of speech that may be useful for a therapist. For instance, the amount of jitter, of shimmer, the duration of breathing cycles in speech that very, very well matches the breathing cycles that can be extracted from breathing belts, for instance, or even the degree of nasalization. All this information may be very useful to therapists to address specific problems. Let me tell you an example. When talking to therapists working with ALS patients, she told me how important the quantizing, measuring the degree of nasalization was, because when the input signals shows lots of nasalization for these patients, this can be a signal that muscular strengths, that the patient doesn't have the muscular strengths necessary to hold the velum up in the up position, in the closed position. So it's always lowered, allowing the coupling with the nasal tract. And this lack of muscular strengths may be an indication that it's also difficult to control the pass of the food that it's swallowed, may go to respiratory channels, and this may be a signal that we need to go to some alternative way of feeding the patient. So there's a lot of potential, in my view, of having discriminative analysis of speech, just as a blood test for many, many diseases. And the second open question is how to collect speech data sets in an era where speech may be regarded as personable identifiable information. So let me tell you also my personal experience. We, together with Caterina and Alberto, we were, and Teresa Paiva, a doctor, a very prominent sleep disorder doctor in Portugal. We tried collecting a data set of speech of patients suffering from either insomnia or obstructive sleep apnea. And we wanted to record a number of things like sustained vowels, breath sentences, but also we wanted to record the questions, their answers to questions about sleeping habits. This was regarded as too private information. We couldn't record it. We had to ask patients to describe an image, Van Gogh's bedroom, in our case. It was the only possibility. We have lots of privacy constraints to build databases that can be used for our work. And I also want to leave you with with this last slide that shows that privacy is not only an issue with paralinguistic tasks. It's an issue with basically all speech tasks. And these are headlines of newspapers or magazines, I can't remember. In 2016 already, there was a headline saying that Siri and Alexa can become witnesses against you in court someday. And this shows reports the case of a person that's accused of strangling and then drowning a house guest after a night of sports TV and a dip in the spa at his house. And he had Alexa on the always listening mode. So we wanted Amazon to provide the recordings of that night, showing that he had nothing to do with the murder. So, in fact, having these devices that are always listening can be can raise lots of privacy issues, and most users do not know that they can turn off the always listening mode, or don't bother doing that. Another example was this headline that more recent, that shows that the Spanish soccer league, La Liga, was recently fined for in an app. This app was using the microphone and the GPS of the football fans' phones to record their surroundings in a bid to identify the bars, which were unofficially streaming games instead of coughing up for broadcasting rights. So they ended up paying 250,000 euros fine, but probably they made more money from these broadcasting rights. I have no idea. But in this age of where everyone is discussing privacy related to things like contact tracing apps, I want to leave you with this cover from the Newsweek magazine, which asks, "Is privacy dead?" Which is a question that we are always now asking ourselves at this time and age. But it's interesting to notice that this is a publication of 1970, as also shown by the type of phones that you can see. But anyway, it's interesting. So before concluding, I just want again to thank my PhD students and their co-advisors. Joanna, Francisco, Catarina, thank you so much. It's wonderful to work with you and with Diksha and Alberto. And all of you, obrigada por toda esta atenção.
Thank you, Isabel. It was a very, very nice talk, very long, very interesting, raised many, many points that I'll be thinking about in the next 3 or 4 years at least. But anyway, I have a few questions, and if the audience wants to pose any questions, I can bring them to you. I have initially, well, your talk had 2 parts. So initially I have a general question on the first part, like you described the construction of this, I think WSM corpus. And I would like to know, how long does it take? How much it costs? How many people involved to build such a corpus?
How many people? A very dedicated PhD student and a bunch of Turkers.
So it's 5 Turkers you mentioned, and one student.
Well, yeah, Joanna spent a lot of work. I think that she can write a paper on how to deal with the agreement between Turkers. It's really an interesting.
Yeah, well, it has always been a problem. Yeah.
It's a talk of its own. Yeah. But the scrapping doesn't take long. Once you learn how to do it, it was quick. I think that when Katerina wanted to do it, she learned it very quickly because she did it later for obstructive sleep apnea. It's very quick. Of course, if you have a small data set, you don't go to Amazon Mechanical Turk. You find yourself and some friends to do the annotation. Yeah, but it's still cumbersome to have to listen, or so it's much easier to look for the claim in the transcription. That's the point. Yeah. And
you kind of, you had the the data in English, and then you had the control in Portuguese. How was
No,
that?
no,
Can
no.
you-
The data was all in English.
all in English.
All
So
in English.
what was that it
Only
showed?
the control conditions data sets. Some of them were in Portuguese.
Oh, okay.
But
Because
it was all in English.
can you transfer? Are we already in a state that we can transfer things from one language to the other?
Yeah. The paralinguistic symptoms, yes. The features, yes. They are maybe not so well, but it works. Especially, we did experiments with X vectors. And our experiments even worked extracting X vectors from an English database and trying them in a Spanish data set. So it works.
Okay.
The speaker characteristics are not so language dependent. Yeah.
Yeah, if you're talking about problems in sleep and voice affecting, probably you affect regularly through languages.
Yeah. I also want to make it clear one aspect is that especially mood disorders and diseases such as Alzheimer's, there's a lot of information that you can also extract from the text. In fact, it can even be more important from the transcription, from what is said. And also from the vision, from the images, from videos, from gait, for instance. Yeah, you can get also lots of cues from there. So, but we were just targeting the speech modality, and then let other researchers then deal with the multimodal videos to address that. Yeah.
Yeah, no, that's good. And for the second part, where you talk about privacy and encryption as a solution for privacy, in what's the scenario that you imagine that kind of encryption can be used? What's going on, where the speaker is, where the analysis is? What's the scenario?
Yeah, as I explained, we still have some, some loose parts in the whole pipeline, because I don't think that right now embarking on a deployment of this with all the features being extracted in the client side will be practical. So features are extracted in the client side. The server has the machine learning model, right? Trained. And the server does not see the audio of the speaker in its raw form. It sees it encrypted, and doesn't see the result of the prediction. It's also encrypted. Yeah, but it's not there yet. It's not practical yet. We have lots of loose ends. That was the word that was escaping. That's lots of loose ends still to address to make this practical. But we have to take the first steps. That's the point. Yeah,
absolutely.
And I do believe that cryptography may be a solution for that. On the other hand, last week I was watching a webinar, a keynote by Joshua Benju, and he was talking about privacy the whole time, and was asked about what about cryptography, and he said, no way, it takes too much time. The computational costs are just not feasible. So he knows the type of networks he's using right now. So it's much more deeper, probably, for a number of things. So
You use basically a feed forward or
Yeah. Yeah, I mean, the neural network was not so what we can call deep. Yeah.
Okay. Well, the general question I have for myself, well, you can protect it with the encryption, etc., but you cannot avoid people using it against you. Say, well, now I can record your voice, I can extract several features of it, and then I don't know how I'm going to use, but I can do that. So well,
what is more scaring is the fact that I have another PhD student which took like 4 minutes of my speech and built a synthesizer that can make me say whatever he wants and I don't want.
So you have these deep fake things going on now, especially in the American election and related topics. So, well, there has been
that spoofing, you know, this or voice cloning or whatever you want to call it, is going to be a huge problem. I don't know if this is going to be solved by watermarks or whatever. I don't know, but it's going to be an even tougher problem than maintaining privacy when we use the Siri and Alexa.
That is exactly
Google Now and all the others. I think it's going to be harder. Yeah.
So watermarking is what I had in mind. Ways of introducing something, saying that you is you or you is not you. Someone on purpose saying, "Well, this is fake, people. Just a joke," or just like they had with Salvador Dali. You can talk to Salvador Dali in a museum in the United States. He has been dead for I don't know how long, but that's clearly fake. Okay, that's fine. But then you get Obama says what he didn't say. That's a bigger problem.
It's a bigger problem, especially if he says that Bush is a wonderful president. No. Donald Trump is a wonderful person. Yes.
Yes. Lovely. Yeah. That's the kind of thing I had. Well, we have had comments from Indonesia's people saying hi. Ardiancia Tahir, I think. Sorry,
I don't see any comments.
No.
No.
This is in another word. But anyway.
No, my chat is empty. How do I see the questions? Or maybe you can read them to me.
Yeah, no, this is just something I'm reading. I have a second screen that's far away. That's why I'm
me too.
This is a kind of a temporary house accommodation. You are in your office, I suppose.
Yeah.
Yeah. Well, we don't have. I think in the past 110 days, I've been to the office once, just to collect some equipment and come back.
No, it's just in this half of the floor is just me and another colleague in a totally separate office. So I walk to my office. I'm privileged, so I can come with no problems. If I had to use public transportation, no way, I would stay at home. It was easier. I wanted to assure that I would have a cabled connection.
Okay. Now, so I invite the audience if anyone has any questions, because well, I have lots of things. But they will be too detailed and too technical for a talk of this sort. Well, just a general question. By looking into these things, have you learned something about language in specific? As this is the Abralin, the linguistic association. So what you have to say, not about sign, but about the language itself. What kinds of insights can you bring us?
So we did a lot of work, especially my colleague Alberto has done lots of work on language identification. and especially on accent identification, automatic one. Mhm.
Oh,
Yeah.
what kind of accents were you looking at?
Uh,
Portuguese,
no,
Portugal?
okay. So I did the work many years ago for Portuguese accents, and I have lots of Brazilians, lots of continental Portuguese, and fewer from African countries, Portuguese-speaking African
Okay.
countries. The Brazilian accents were very easily distinguishable, very much.
Yeah.
The European and African ones, continental Europe, I mean, and African ones were more easily confusable. Both with the African was confusable with both the European and the
Oh,
Brazilian.
really?
Yeah.
Oh,
I was really interesting. But Alberto has been working with the data that's provided by challenges, international challenges like NIST. NIST does this sort of thing, and he even participated and won the first prize for being able to detect what was the first language of someone talking in English. And that was really interesting because I listened to some of these recordings, and I think I have a good ear, but I couldn't tell.
Of course, once that happens to me,
yeah.
I was listening to someone give a talk in English, and I knew that person was a Brazilian, but immediately from her English accent, I could say she's from Rio. There was no doubt about it.
Yeah, I also used to say that, but it's much harder when you're faced with lots of recordings from languages that you don't know.
Yeah.
And then you get confused with so many different
You don't know what pattern to match to that
yeah,
language. Yeah.
definitely. Yeah.
Yeah. Yeah. Okay. Well, thank you. Well, thank you for the lovely talk. Thank you for the lovely discussion afterwards.
Thank you for the opportunity. Thank you for the invitation. It was a real pleasure. And I look forward to seeing you all very soon when this whole mess ends.
Oh, yes,
and,
absolutely.
And stay safe, all of you.
Yeah, same for you. Okay, bye-bye. Thank you very much. Thank you very much.